Hey, Chem friends. Welcome to the first Unit 5 screencast. It's the third day of the first week, which means if you're in D, E, or F block classes, then it should be Thursday, January 21st, 2021. And if you're in A block class, then I think it's Monday, January 25th. I'm obviously recording this a little bit early, and hopefully the schedule hasn't changed so much that we're not able to do the screencast. I have been stressed about this unit all year, and I'm sure, as I've said, you just got to bear with me, and I promise it'll go well. So please be taking the guided notes, watching these screencasts, and following along. It's super important because this unit is on stoichiometry, which is, a scary word. And the unit is complicated if you let yourself fall behind. So please don't fall behind, and I can almost guarantee you're going to do just fine. So bear with me here, and we'll get through it together. I've got my guided notes open, and you should have yours as well. We're in Unit 5, and we're in 4.1, which is on this concept of the mole ratio. I've never defined the word mole, and I'm actually not going to define it today either. We won't really talk about what a mole is until next week. So instead, what I want us to be able to do is relate the amounts of reactants and products together. If you start with a certain amount of reactant, how much product is going to form, which we're going to wrap up in 4.4. So bear with me. Now, by the time you walk out of here this week, I want you to be able to use the coefficients from a balanced chemical equation to talk about the relationships between reactants and products. We did this on day 2 when we used that simulation about sandwiches. And then I want you to kind of talk about what a mole ratio is and how it relates to the law of conservation of matter. So let's get into it. Remember, guided notes open. Chemical equations, and what's so important about them and why we had to balance them was because it tells us the relationship between reactants and products. So for example, if this was our chemical equation about bread, cheese, and sandwiches, which is the chemical equation from the simulation on day 2, what the coefficients tell us is if you start with 2 pieces of bread, then you're going to end up getting 1 sandwich. So they're in a 2-to-1 ratio. Therefore, if you started with 4 pieces of bread, you're going to get half as many sandwiches. You're going to get 2 sandwiches. If you started with 10 pieces of bread, you're going to get half as many sandwiches, or 5. Likewise, if you started with 5 pieces of cheese, you could get 5 sandwiches out of that. Now, those coefficients are the exact same idea in a balanced equation. Notice these coefficients are different, but what it's saying is that if you start with 2 molecules of hydrogen, then you're going to get out 2 water molecules. So if you started with 10 hydrogens, you're going to get out 10 waters because they're in a 1-to-1 ratio or a 2-to-2 ratio. Whereas for every oxygen, you get out twice as many waters. So if you started with 5 of these molecules, then you're going to get out twice as many as those molecules. And that right there is called a mole ratio. The coefficients in the balanced chemical equation allow us to create equivalency statements to see the relationship between reactants and products. So the coefficient is the number in front. The 2 in front of the H2 tells us, well, for every 2 hydrogen molecules, we're going to get out 2 water molecules. And knowing that means we can create equivalency statements. And once we have equivalency statements, we can write conversion factors. So let's try that. This is the same equation. 2 hydrogen atoms plus 1 hydrogen atom makes 2 water atoms or molecules. I will use those terms interchangeably. They do mean slightly different things, but as long as you care, atoms and molecules in this class are going to basically be the exact same thing. So don't get confused, like the law of conservation of matter and the law of conservation of mass. So what I know from this is that for every 2 molecules of hydrogen, I can get out 2 molecules of water. They're equal to each other. It's called an equivalency statement. And if you can write an equivalency statement like this as an equal sign, then you can write it as a fraction. So how do you do that? Well, this is like saying 100 pennies is equal to $1. So you could write a fraction where 2 molecules of H2 is on the top and 2 molecules of H2O is on the bottom. Remember, they're equal to each other. So instead of writing 2 molecules of H2, you could plug in 2 molecules of H2O right here. And then you've got 2 molecules of H2O over 2 molecules of H2O, which just means 1. Equivalency statements are just, they're fractions that mean 1. And you could also flip this fraction over and say for every 2 molecules of H2O, I get out 2 molecules of H2. Where the equal sign is, that's where your divide bar goes for your conversion factors. So this is your equivalency statement, and then this is a conversion factor, but I'm not going to quiz you on those terms. So as long as you know you can take an equal sign and turn it into 2 fractions, you're going to be just fine. So let's try a different one between oxygen and water. What we know is that 1 molecule of oxygen is equal to 2 molecules of water. So how could you write these 2 fractions? And you need to write them in your guided notes. Did you think about it? I hope so. We can put 1 molecule of oxygen on the top and 2 molecules of water on the bottom. Remember, 1 molecule of oxygen is equal to 2 molecules of water. So we could just plug this in instead of writing 1 molecule of O2. And what we're just saying is that 2 molecules of H2O over 2 molecules of H2O, which is just a fancy way of writing 1, really. Equivalency statements, because they're equal to each other, allow us to convert without changing any of our values. Just change our units. So we could also write this fraction with H2O on the top. How would you write it with H2O on the top? Well, yeah, you just flip it over. So 2 molecules of H2O give us 1 molecule of O2. And if you've forgotten Unit 1, you might be thinking, Misty, why are we going over conversion factors? We did this back in Unit 1. I thought we were done. We're not done with conversion factors. In fact, we're going to use them every single day in this unit to do problems like this one. So if we're starting with 50 molecules of oxygen, how many water molecules are produced? Well, we can just use logic here, right? Because for every 1 oxygen molecule, we're going to get out 2 water molecules, twice as many. So if we start with 10 of these, we'd get out 20 of those. If we started with 20 of these, we get out double, 40 of those. If we started with 50 oxygen molecules, we should get out 100 water molecules. That's logic, which is awesome. And you should always use logic to just make sure you're on the right track. But I want to use the proper scientific calculations to solve this problem. And those calculations were centered around this chart back from Unit 1. Do you recognize it? Well, if you dropped into this class, you probably don't. And if your memory isn't that of an elephant, you might have also forgotten. So I just want to go over it really quickly. I call this the from to from chart, and it allows us to do dimensional analysis problems. Dimensional analysis problems let you cancel out your units. In the left boxes, you'll put the given, and in the right boxes, you'll put your equivalency statements written as conversion factors. So I think the best way to do this is just to try a problem. So let's try it. In this problem, the given, how many water molecules are produced if 50 molecules of oxygen react? So my given is 50 molecules of O2. I'm going to put that in the given box, in the top left box. Now, some people are confused why the bottom is empty. That's because we don't have a fraction in our given. We're just starting with oxygen. So it's 50 molecules of O2 over 1. You could put a 1 here if you wanted to, but notice I didn't make that box yellow in your guided notes. You could leave it just blank if you wanted to. Now, remember, the from units are going here. That's what we're converting from. We're converting from molecules of oxygen to what? What do we want to convert to? Well, that's what you're trying to solve for. How many water molecules? So in the to box, I'm going to put molecules of water. And in my from box, those are the units I'm converting from. That's molecules of oxygen. If you've forgotten these units, and these units will always be the same because they're both froms. These units have to cancel out. So whatever units you have in the top left are going to go in the bottom right. What we need to know is the relationship between molecules of water and molecules of oxygen. We call this an equivalency statement, and we actually wrote the equivalency statement in our notes right above on the right side of the page. The relationship between molecules of oxygen and molecules of water. We said for every 1 molecule of water, you're going to get 2 water molecules, in which we wrote as 2 fractions. 1 molecule of oxygen for 2 molecules of water, 2 molecules of water for 1 molecule of oxygen. Remember, they're equal to each other. They mean the exact same thing. But we only want 1 here, and we want to use the conversion factor that has water on the top and oxygen on the bottom. So which of these conversion factors has water on the top and oxygen on the bottom? That one, right? It's got water molecules on the top and oxygen molecules on the bottom. So what we're saying is that for every 2 molecules of water, we get 1 molecule of oxygen. Now, don't be confused. That vertical bar just means multiply, and I put it in a chart to help you organize your units so that they cancel out. The whole goal of dimensional analysis is to cancel out your units. So what I mean by that is we have molecules of oxygen in the top, molecules of oxygen in the bottom. Remember, they're both from boxes. They're supposed to cancel out. And what we're left with is just molecules of water. How many molecules of water? 50 times 2 is 100, divided by 1 is 100. And isn't that exactly how many we said? Because they're in a 1 to 2 ratio. So if you start with 1 of these, you get double. If you start with 50 of these, you should get double, or 100. This right here, this equivalency statement, is called a mole ratio. But again, we're not going to define mole until next week, which I know is weird, but look at the word molecule, mole. There's something going on there, and we'll talk more about it next week. So what is a mole ratio? Well, a mole ratio is a conversion factor. So it's an equivalency statement that relates the amount of reactants and the amount of products in a balanced chemical reaction. Get that definition down. It's a conversion factor, so it's an equal statement. It says for every 2 molecules of water, we need 1 molecule of oxygen. Those are equal to each other. It relates reactants, the things you start with, and products, the things that are produced. How does it do this? Well, mole ratios use the coefficients from the balanced chemical equation to determine the equivalency statement. So in that last little unit, unit 4, we were balancing equations and doing reaction types. The reaction types, put those on the back burner. We're not going to do reaction types in this unit, but you need to balance the equations to follow the law of conservation of mass, because you need to get these equivalency statements, these conversion factors. You need to know if you start with 1 oxygen, you get 2 water molecules. If you start with 2 hydrogens, you'll get 2 water molecules. You need to know the conversion factors, and that conversion factor comes from the coefficients in the balanced chemical equation, which we got using those charts. The balancing isn't going anywhere. In fact, it's step 1 of this new unit. So if you struggled with balancing last unit, we got to figure this thing out, because you're going to need to be able to balance the equations to write the mole ratios. But we have all unit to figure this thing out. We have like 4 weeks to get this done. So for the rest of the day, what I want you to do is do the Google form on understanding mole ratios and equivalence, making sure you can use those dimensional analysis charts to get your units to cancel out. And as always, if you have questions, let me know. I'm here for you, and I'll see you next time.